Imagine this. It's the middle of the night, and the city is alive with activity, lights glowing, homes warm, devices charging. But what if all of this was powered by the sun? That's right, even though the sun set hours ago, it's still fueling everything around you. This might sound like magic, but it's actually the promise of a groundbreaking idea called space mirrors, a technology that could change how we think about energy forever. Solar energy has been a game changer in our push toward cleaner, more sustainable power. But there's one major problem. It stops working when the sun goes down. We've all experienced it. Solar panels soaking up the sun's rays all day, only to go silent at night when we still need electricity. This reliance on daylight has always been the Achilles heel of solar power. But imagine if we could fix that. If solar power could keep going around the clock, no matter the time of day. That's where space mirrors come in. Picture giant mirrors floating high above the Earth, catching sunlight and redirecting it down to solar farms, even at night. It's like having a giant flashlight in the sky, ensuring that solar panels can keep generating electricity long after sunset. This isn't just a futuristic idea, it's a bold and innovative concept that could make solar energy a reliable 24/7 power source. Let's dive deeper into how this works. Imagine these mirrors as enormous floating sheets of reflective material positioned in space where they can always catch sunlight. The key here is that they're placed in special orbits designed to keep them in the right position to reflect sunlight to specific spots on Earth. Think of them as a carefully orchestrated team of mirrors, each one adjusted with precision to ensure that sunlight hits its target even from thousands of miles away. Now, you might be wondering, how big are these mirrors? To give you an idea, imagine something the size of a small city floating in space. These mirrors would be made from lightweight, super reflective materials capable of withstanding the extreme conditions of outer space. The sheer size of these mirrors would be staggering, potentially spanning several kilometers in diameter. They would need to be this large to capture enough sunlight and redirect it effectively over vast distances, turning night into day, at least for solar panels. It's not just about bouncing sunlight back to Earth. The real magic happens in how precisely these mirrors are controlled. Imagine trying to shine a flashlight on a tiny spot from miles away. That's the kind of accuracy we're talking about. Advanced technology, including artificial intelligence, would be constantly at work, adjusting the mirrors to ensure that the sunlight is always directed where it's needed most. This precision ensures that the energy from the sun is spread evenly across solar panels, maximizing their efficiency without causing damage. Let's break this down even further. These mirrors wouldn't just float aimlessly in space. They'd be carefully placed in what's known as a geostationary orbit, about 36,000 kilometers above the Earth's equator. This orbit allows the mirrors to remain fixed over a particular point on Earth, constantly reflecting sunlight to that specific area. Alternatively, some mirrors could be placed in a sun-synchronous orbit, moving in harmony with the Earth's rotation to ensure continuous sunlight reflection to different regions. The result? Solar farms that receive sunlight even in the dead of night. And it's not just about technology, it's about transforming the way we use and think about energy. Imagine a world where solar power isn't just a daytime resource, but a constant, reliable energy source, available whenever we need it. This could dramatically reduce our reliance on fossil fuels, cutting down greenhouse gas emissions and helping to combat climate change. Think about the impact on communities that currently struggle with energy access, places where the sun doesn't shine as brightly or as often. Space mirrors could bring clean, renewable energy to these areas, powering homes, businesses, and schools around the clock. But like any ambitious idea, space mirrors come with challenges. Building and launching these massive structures into space is no small feat. It's going to require significant resources and international cooperation. The costs are high, but so are the potential rewards: clean, reliable energy for everyone. The engineering challenges alone are immense. First, there's the question of how to build mirrors that are both large enough and light enough to be launched into space. Engineers would need to design these mirrors in modular pieces, allowing them to be assembled in orbit. This reduces the complexity and cost of the launch, but it also introduces new challenges in terms of assembly and maintenance. These mirrors must also withstand the harsh environment of space, including extreme temperatures, radiation, and the constant threat of micrometeorite impacts. Then there's the issue of precision. The mirrors must be accurately aimed to reflect sunlight onto specific areas on Earth, requiring highly sophisticated control mechanisms. These systems would need to account for the dynamic nature of both the Earth and the satellites. Factors like orbital decay, gravitational perturbations, and atmospheric conditions. Advanced propulsion and control systems, possibly utilizing AI for real-time adjustments, would be essential to maintain the correct orientation of the mirrors. Maintaining these mirrors in space is another significant challenge. Space is an unforgiving environment with risks such as space debris collisions and exposure to radiation. These factors can degrade the mirror's surfaces and compromise their effectiveness over time. Developing resilient materials and self-healing technologies, as well as implementing strategies for regular maintenance or replacement, will be crucial to the long-term success of space mirrors. There's also the financial aspect to consider. The cost of deploying and maintaining a network of space mirrors is a major consideration that could make or break the feasibility of the project. The expenses involved can be broadly categorized into research and development, manufacturing, launch, and operational costs. Research and development alone could run into billions of dollars as it involves creating new materials, engineering solutions, and testing prototypes in space. Manufacturing costs would also be substantial, particularly given the scale of the mirrors and the need for precision engineering. Launching these massive structures into space would likely require multiple missions, each costing hundreds of millions to billions of dollars, depending on the number of mirrors and the choice of launch vehicle. Given the size and weight of the mirrors, heavy lift rockets or even new launch systems might be necessary. Once deployed, the operational costs would include maintaining the mirrors' positions, ensuring their reflective surfaces remain intact, and possibly replacing damaged components. These ongoing costs could be significant, particularly if the mirrors require frequent adjustments or repairs. Overall, while the concept of space mirrors is technologically intriguing, the cost remains a formidable barrier. Large-scale collaboration, possibly involving multiple governments and private entities, may be necessary to share the financial burden and make the vision of space mirrors a reality. Beyond the technical and financial hurdles, there are environmental considerations. Launching and maintaining these mirrors could contribute to space debris, which is already a growing concern. Even a small increase in space debris could heighten the risk of collisions with other satellites, leading to a cascade effect known as the Kessler syndrome. This phenomenon occurs when the density of objects in low Earth orbit becomes so high that collisions become more likely, potentially rendering space travel and satellite operations hazardous. Additionally, the introduction of artificial light during nighttime hours could disrupt natural cycles for plants, animals, and even human populations. For instance, altering the natural day-night cycle could confuse nocturnal animals, disrupt migratory patterns, and affect the growth and reproduction of certain plant species. These are significant concerns that need to be addressed as part of the development and deployment of space mirrors. But despite these challenges, the potential benefits of space mirrors could be substantial. By providing a constant source of renewable energy, they could reduce our reliance on fossil fuels, lower carbon emissions, and help combat climate change. This could be especially impactful for developing countries, where energy poverty is a significant barrier to economic growth and improving living standards. By enabling 24/7 solar power, space mirrors could empower communities, support local industries, and enhance overall quality of life. Moreover, this technology could reduce the geopolitical tensions associated with energy resources. Nations would be less dependent on fossil fuel imports, leading to a more stable and equitable global energy landscape. However, the rewards could be nothing short of transformative, not just for how we power our world, but for the future of our planet. Thanks for sticking with us on this deep dive into space mirrors. If you're excited about the future of renewable energy and want to stay updated on the latest technological breakthroughs, make sure to subscribe to AI with Win. Your support helps us continue exploring the ideas that could shape our world. See you in the next video.